Welcome to the office. We want to continue working with cycles in our discussion of the group of permutations. Now, we gave an example where the permutation was exactly a cycle. But in our previous examples, we talked about permutations that had orbits where many of the orbits did not have just one element in them, right? It's not that there was one orbit that had more than one element, there were many. Those are not cycles, right? Those permutations themselves are not considered cycles. So then the question is was there a way to represent each permutation as a collection of cycles? And yes, there is. So we're going to take a look at a theorem that makes that statement, and then we're going to go ahead and take a look at an example and decide for ourselves how we can observe this permutation as a product of cycles. But in particular, what we're interested in is observing each permutation as a product of disjoint cycles. So yeah, let's look through that in a minute. So every permutation of a finite set is a product of disjoint cycles. And we can do that by recognizing, so this is an example that we took a look at earlier. We looked at the orbits of this, and let's just quick remind ourselves of what they are. 1 goes to 4, and 4 goes to 1, so that was the end of that orbit. The next orbit was 2 goes to 2. That's fine. That looks wonderful. 3 goes to 10. 10 goes to 7. 7 goes back to 3. So that's the end of that orbit. And then we have our next orbit of 5 goes to 9. 9 goes to 6. 6 goes to 8. And 8 goes back to 5. So that takes us back to there. And then the last one is just the element, not just the element 10 that appears over here. So that should be everything. We can verify that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wonderful. So that's one of the nice things about orbits or this notation. We know that everything has been handled. Okay, so it's easy to verify that we have everything there. Now, if I wanted to consider the permutation that has this as, right, the cycle that has this as its only orbit, well, that would be the cycle 1, 4 in cyclic notation. This we don't need to bother writing down, right? That's just, it's fixed. That's no problem at all. This we can observe as, right, if this were the only if it were the only orbit that had more than one element in it, that would describe the cycle 3, 10, 7. And if this were the only orbit that had more than one element, that would describe the orbit, that would describe the cycle 5, 9, 6, 8. So this orbit tells us about this cycle. This orbit tells us about this cycle. This orbit tells us about this cycle. Okay, again, sigma takes 1 to 4, sigma takes 4 to 1, sigma takes 3 to 10, sigma takes 10 to 7, sigma takes 7 to 3, and so on. Set notation, order doesn't matter. We want it to matter, so we write it in this cyclic notation. Ordered sets, right? Ordered collections here. All right, so we end up with that. Now, if I were to call this maybe sigma 1, I could call this sigma 2, and I could call this sigma 3, right? We have definitions for sigma 1, sigma 2, and sigma 3. There's no issue there. But if I were to compose them, if I were to compose them as sigma 1, composed with sigma 2, composed with sigma 3, technically it's sigma 3 composed with sigma 2, composed with sigma 1 there, because we compose from right to left. But this would be, each of these things is represented exactly by that, which is 1, 1, 4, 3, 10, 7, and 5, 9, 6, 8. And if we were to consider the orbits of this, well, that's pretty easy to do, right? The orbits of this are exactly these. Now, having the same orbit doesn't mean it's actually the same permutation, so you got to be careful about that. However, what it does do for us is it allows us to recognize that sigma or sigma itself, we can express as this composition, sigma 1, sigma 2, sigma 3. Now, composition in general is not commutative. However, each of these cycles are disjoint from one another, and that's largely, or very much so, due to the fact that they were given from the orbits, which create a partitions. Therefore, they must be disjoint from one another, which is how we know we can create any permutation as a disjoint product of cycles. So that's awesome. That's wonderful. But since they're disjoint, the order actually doesn't matter, because whether I list this thing first or this thing first or that thing first, it's still taking 1 to 4, 3 to 10, 10 to 7, 5 to 9, 9 to 6, 6 to 8, and 8 to 5, right? It's still doing the same thing. So I can actually write sigma itself as the 1, 4, 3, 10, 7, as it's written there, 5, 9, 6, 8. And it doesn't matter if I write this as 3, 10, 7, 1, 4, 5, 9, 6, 8, because I haven't changed what's happening. Taking 5 to 6, 5 to 9, 9 to 6, 6 to 8. That's still true here. I'm taking 3 to 10, 10 to 7, 7 to 3. Well, that's still true here, right? I'm not, because they're disjoint, I can order them however I want. If they're not disjoint, then we cannot order them however we like. And we'll see that in a little bit here, because we're going to revisit an example from, let's see here, the last section, I believe it was, where we take two permutations and we compose them in opposite orders. And we're just going to use the so we're going to use the cyclic notation now, the cycle notation for those permutations. And that should be our next example. Yep. So I think these are the same orbits that or the same permutations that we looked at in a previous example. So we'll return in our next video for an example, for that example here.